Hello, class. Yes, I am. My microphone is recording this time. I'm going to double check that. Yes. What I want to do now is to bring it all together. Everything that we've learned about centroids, about moments of inertia of cross-sectional areas, about shear force and bending moment diagrams are all going to come together as we work through, I think it might even be 2 lectures. I've got 2 good examples that I want to share with you. So first of all, let's look at the loading. It's going to be a simple beam. So you're going to have to think back to, let me just see how many things I've got there. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right. 1, 2, 3, 4, 5. 1, 2, 3, 4. Who knows where 5 is, but let's say it's someplace right here. All right. We've got 2 reactionary forces, R sub A, just like we have always worked with before, R sub B. And we've got 3 forces that are actually symmetrically placed on this beam. And each of these forces is 10 kilonewtons. So, you know, I'm making this so that each one of these should be relatively easy so that we can get the process down. Now, let me drop these down for when we make our shear force and bending moment diagrams, right? Now, I think that in summing, R sub A and R sub B, I think everybody can see are going to be equal in this case. So when we sum the forces, R sub A plus R sub B, they're going to be equal to 30 kilonewtons. And I'm going to actually even, we can, let's sum the forces. I want to make sure I leave enough room here. And I might just sum the forces because I need a little more, room for the other things. Right down here. So, why don't I do it up here? So I'm going to sum the forces, or the moments. Did I say forces? We've already summed the forces in the x direction, and that gives us R sub A plus R sub B, right? So forces in the y, did I say x direction, equals 0, and that's R sub A plus R sub B minus 30 kilonewtons, and of course that infers that equation that we got right there. I don't think that I have to, what's the word I want there? Take a lot of time to, I'm sure it's just snapping into your mind right now. So let's sum the moments about B equal to 0 this time. So if we look at R sub A is going to be clockwise around there. So it's going to be minus R sub A, right? I'll just put a bracket there. The minus is outside of the magnitude that I am, determining right now, times 10 meters. And then I've got 10 kilonewtons times 8. So this one right here, and this would be going clockwise. So plus 10 kilonewtons. I'll put the brackets around it later, times 8 meters. Right, everybody see that? And then I've got this for 5 meters and this for 2 meters. So let me just write these in. So I've got another 10 kilonewtons for 5 meters. I'll just put a box there. Plus, just waste a whole line. I might have been able to go underneath, but I'm not going to. I'm going to put that there. Right, plus 10 kilonewtons times 2 meters. All right. And what that tells us, if we add all these up, let's see, that's 80 kilonewtons, 50 kilonewtons, so that's 130 times 20, that's 150. 150 divided by 10, so this tells me that R sub A equals 15, and of course we knew this, kilonewtons, and of course R sub B equals 15 kilonewtons, right? So we can easily draw our shear force diagram. All right, let me just drop that last one down. We can easily draw our shear force diagram. Well, I didn't even get it all the way over here, did I? All right, so if we look at our shear force diagram, let me do this in red so that you can see what I'm doing at each point here. You can see R sub A is going to be 15 kilonewtons, right? So right here I'm going up 15 kilonewtons. I'll just put K because I've got such a thick red pen here. I did buy new pens, but I'm going to save those. Okay, so 15K. Then I'm going to go across. I'm going to go down 10K. So I'm going to go across at 5K. And I'm going to go down 10K. Wait a second, what have I got here? R sub A, 30, 15, 10, up 15, down to 5, over across to 5, down 10, so I'm on plus 5, going across, or minus 5. Then I'm going across, then 10 more, bring me down to minus 15, then 15 up brings me back up to 0. Does everybody see how I did that? Oh, I didn't really draw that far. I think I made that and that too long, and this not long enough. But you get here's my disclaimer: not to scale. All right, now what we can use is we can use the area under the curve for the shear stress. Let me just write shear stress down there so we know what we're doing. In fact, I can use this sign. So that's going to be my positive shear stress and my negative shear stress via our convention of Ruck on one side and Leduc on the other side. So when we do that, we then find out that we've got this. We want to come up with, you know, some things here too to show how much we have under the curve at each of the different times. So if we look at this right here, I think everybody can see that we're at 15 by 2, so that's 30, right? 15 by 2, 15 kilonewtons by 2 meters is 30 kilonewton meters, right? And then here, this is going to be 5 kilonewton meters. And down here, I've got minus 5 kilonewton meters. And then here I have, I'll just try and draw it out here, minus 15 kilonewton meters in that square. So we've broken it up into 4 different squares that are constant. You know, they are squares, we know what they are. So what we can do now is we can do our bending moment diagram right underneath this. I'm just going to pull all of these lines down here to give me a little more room. And let's say that this is our bending moment diagram, right? And I'm going to draw this in, God, what color can I find here? Well, I don't know, there's a purple. I don't think purple comes out as black, probably. So wait a second, let me actually write on here what it is that we're doing. So we're doing the bending moment. That's the positive. This is the negative. We're going to see there is no negative for this. The bending moment is all positive here. So when we do it, the first thing is 30 kilonewton meters. So we know that we have to be up to 30 kilonewton meters, right? We're going up here because we're coming from 0. We have to have 0 at both ends. So we're going up. That's positive slope, right? So positive slope of 30 kilonewton meters. How many meters am I going? Well, wait a second. We already got that. 30, yeah, 30 kilonewton. I already figured it out. 2 times 15. Yeah, I've already figured it out because it's the area under the curve. So we're going up to 30, right? Does everyone see that? And this is 5, but I have it for 3 meters. What was I doing? I'm sorry, I got that one wrong. Where's my green? Okay, so 15 times 2 gives me 30. 3 times 5, boy, that was easy, thank God. That's plus 15, I'll put a plus there. And then this is going to be minus 15 because I've got 3 times that. And of course, this down here is not minus 15, this is minus 30. Oh, look at how I did that, kilonewton meters. Thank goodness, and I'm glad that everybody caught me on that one and was paying attention. Oh, you think I did it on purpose? No, I actually didn't. So anyway, this is now going up 15 more, right? Now, all of a sudden, it's going down 15. And then here, it's going down 30, right? Oh, I'm sorry. There we go. So what is this up here? That would be plus 45 kilonewton meters, wouldn't it? This down here, when actually it's really killing, you know, these are the points on this line. That would be at 30 because I've got to go down minus 30, right? And then this is down from 45 at 15, right? 5 per things, and that's what's happened there. So that's the slope of that line. And the 5 is the slope of the line, and of course the area under the curve is what I've got here. So let's just make let's put this in purple too. So this is plus 5 kilonewtons, right? Everybody knows that. This is plus 15 kilonewtons. This is, and this is of course where I screwed up, of course, minus 5 kilonewtons, and this here is minus 15 kilonewtons. But what is that really when I say with minus 15 kilonewtons? What that is really the slope. What that is kilonewton meters per meter. So when I say kilonewtons, right, up here, where can I write that? When I have kilonewtons on the shear force, when V equals, let's say, minus 15 kilonewtons, what that really equals is minus 15 kilonewton meters per meter. See how the meters then cancel out? So this represents this line here, but it also represents then the slope of that line integrated into the bending moment diagram. All right, so what we're looking at right now is a maximum, right? What's our maximum bending moment? Right there, 45 kilonewton meters. So we want to see if this cross-sectional beam, and I haven't gotten to that yet, but I'm going to do that right now. So I'm going to look at an I-beam, and this I-beam, let's see where I can draw it. I'll draw it right here. Wow, that looks like a really, where did I get that one? This I-beam is going to have a cross section. 1, 2, 3, 4. Is that when? Wait, that's 2 point. Just a second. 20. I have 25 centimeters there. Yes, I do. 25 centimeters. So, 1, 2, 3, 4, 5. There we go. And then the center web is 5. So, and we're going to 1, 2, 3, 4. I'm trying to draw this to scale. I don't have it drawn to scale on my thing here. I just have, you know, my horrible drawing that I put up there. But now I've got it drawn to scale. So this is 5 centimeters, right? This is 20 centimeters. As you can see by the drawn to scale drawing that I have, 25 centimeters. All right. And that beam is going to be holding up this bridge that we've got here, this 10 meter. I mean, this is 10 meters, so that's 30, feet long, 30 feet long. And I'm going to use this one I-beam to hold that whole thing up. You think it's going to work? Let's see. Let's see. So, I mean, I can always find some material that's going to do it. So we're looking at this cross section here. I think everybody can see what I'm. This is the cross section that I'm working on, and I have to find out a couple things about this cross section. I've got to find out what the total area of this cross section is, right? So let's separate out. This is actually a great pen. I'm going to use this. Maybe I picked up the wrong pen before. But I want to separate this area that we've already done. So now we've found the maximum bending stress. We've done our shear stress and bending moment diagrams. And now what we're doing is we're working on our cross section of this beam. I'm going to use this new one. It's fantastic. I don't know where I got where it came from, how long it'll last, but I'll use it. All right. So we want to do a couple things. We want to find out where our neutral axis is, right? So where is our neutral axis? And I think that everybody can see right here from what we've got that our neutral axis is going to be right in the center of this beam. Now I could change that so the top isn't quite as large so that we would get a neutral axis that's off. But for this first problem, even though I'm going to go through it, I want everybody to notice that, you know, this is symmetrical about this, right? So if this is 20 centimeters, 5 centimeters, and 5, then right in the middle of this 20 is going to be our neutral axis, right? I'll just draw the neutral axis in there right now, right? This is going to be our neutral axis. So we don't really have to determine it right now, but I want to go through the process of determining our neutral axis because the neutral axis is the centroidal axis, right? And so where is that and how do we do that? Now, here's what I'm going to do. I'm just going to come down here. I'm going to draw, you know, a line, just you know, X and Y axis. And we're going to look at 3 separate rectangles. This rectangle right here, this rectangle in the center, and this rectangle down here. We're going to find the individual centroids of these 3 rectangles. Let's call this rectangle 1, rectangle 2, and rectangle 3. We're going to find the centroids of those, and then we're going to divide it by the total cross-sectional area, and we're going to figure out what the centroid of that is, just as if this wasn't symmetrical about this. I think everybody can see that the centroid would be 1, 2, 3 up here. It would, since this is 30 wide, it'd be right in the middle, 15 centimeters up, right? And that's what we're going to find out. So in doing this, to determine where the neutral axis is, we want to find the centroidal axis. So let's take our individual things. We know this. We know the overall centroidal axis of that composite body times its total area is going to equal the sum, and we've done this before in statics, the sum from I equals 1 to n of the individual centroids of those y sub I times a sub I, right? So let's just sum all of those up. The first one is going to be right in the center. So, you know, this would be the centroid of that first one would only be 2.5, because that's 5 centimeters thick. So it'd be 2.5 centimeters high, right? So I've got 2.5 centimeters. We'll do it in centimeters, right? Times the area of that. Well, 5 centimeters by 25 centimeters is 125 centimeters squared. Okay, that's the first one. Let's do the second one. Well, the second one is going to be a bit higher because now it's right in the middle of this, and that's 5 centimeters plus 10 centimeters, right? Because this is 20 centimeters across here, so the middle of it's going to be 10 plus 5, so that's 15. So 15 centimeters times, and this is 20 by 5 centimeters, so that's going to be 100 square centimeters, right? And then the last one, I'll just put that one down here, is going to be, well, where's the centroid here? Well, that's about 2.5, right? The centroid for this is 2.5 above where it is now. So let's see, 5, 20, 25 plus 2.5 gives me 27.5. Right, 27.5 centimeters times, well, 25 times 5, that's 125 centimeters squared. Right? Okay. Now we also have to find out what the total area is, because we want to find out y bar, don't we? So we really want that sum divided by a total. What is this sum? Let's see. 2.5 times 125. Wait, I've got my handy calculator right here. 2.5 times 125 is 312.5. I don't know why I couldn't do that in my head. 312.5, and what are our units? Centimeters cubed. Let's keep, you know, when we're not using primary units, let's definitely keep our units in check. Well, 15 times 100, how about 1500 centimeters cubed? And then 27.5, I better use the calculator for this, times 125 gives me 3437.5 plus 3437.5. All right, centimeters cubed. And we want to divide that by the total cross-sectional area. Now let's just do this. We've got this 5 times, well, we've already done it. 125, 100, 125. 125 plus 125, 250. Plus 100, 350. So we've got it divided by 350 square centimeters. And so what this gives us is y bar, and I hope to God y bar comes out to 15. Let's do this. 312.5 plus 1500 plus 3437.5 divided by 350 gives me 15 exactly. Thank goodness. 15 centimeters. And that is, you know, us showing. Now, the same process. What if, like I said before, what if instead of it being like that, what if the top was shorter, right? Like this, like a rail, you know, railroad rail. Then you would find out that the neutral axis is a little bit lower than 15 centimeters, wouldn't you? And in fact, we'll probably do an example similar to that in the lecture after this, because I want to do a couple examples of flexure. I mean, you know, we're putting it all together here. Everything that we've learned in statics and everything else is all coming together. So we know it's 15 centimeters. So that's where it is. Now, that also tells us something. What is Y maximum, which I also call C? right? Because our equation, let's not forget, sigma equals my over I, right? That's what we're looking at. We want to find out our maximum bending moment. So we know that. Why don't we write that in there? M maximum equals 45 kilonewton meters. All right. So we've got M out of the way. And put a little tick over M. How about Y? What is the maximum? What's the maximum distance from this neutral axis to the top of the beam? What is that distance? I think everybody can see that it's 15 centimeters, isn't it? But you know, did I write, you know, I wrote this as kilonewton meters, but I'm not going to write that in the equation, right? It'll be 45 times 10 to the whatever. I'm not going to write this as centimeters either. Now, that we're getting up there. So Y maximum, we got that maximum, we got this maximum, is 0.15 meters, right? Okay, so everybody, 15 centimeters equals 0.15 meters. There you go. So the last thing that we've got to find out now is the moment of inertia of that cross section, and that's going to require the parallel axis theorem, right? So I of x prime equals I of c prime plus cross-sectional area, the total cross-sectional area, times d squared. There you go. I'm pulling that out there. D squared. Yep. We don't want to lose the square, so let's you know, box that in with red to make sure that everybody knows that that equation includes the square. All right. Now, we're going to have to use that because we've got to bring them all to the neutral axis. What I'm trying to find here is I about the neutral axis. And so what I'm going to do is I'm going to take I of 1 about the neutral axis, I of 2 about the neutral axis, which should be easy because the centroid of this is right in the neutral axis, and then I of 3 about the neutral axis. So I'm going to have to find it about its centroid, then I'm going to have to move it down to the neutral axis. And I'm going to have to find I about this centroid, and then I'm going to have to move it up to the neutral axis. You see what I'm doing? How I've got to use the thing. So what are these distances d that I'm going to be moving this to the neutral axis? Well, let's see, this is 2.5, right? And the neutral axis is 15. So wouldn't that be 12.5 centimeters? That's what my distance is going to be when I move those to the neutral axis. All right? Okay, just a second. I'll be right back. Okay, sorry about that, but had to do something. And let's get back to the rectangles and bringing them to the neutral axis. Now, I of a rectangle equals, and this is about the centroidal axis, is BH cubed over 12, right? BH cubed over 12. I should double check that. But I mean, I used it to solve the problem, so I'm pretty sure that that's what it is. And no, I didn't even find the right one. Oh well, I'm going with that. BH cubed over 12, and I think about the base, it's BH cubed over 3. I think I even derived this for you, so I'm going to go with that. So for this rectangle down on, or let's do the rectangle right in the middle. Let's do I of 2 first. I'll put an arrow there, and then we'll do I of 2. And I of 2, since the centroidal axis goes right through there, we don't have to use the parallel transfer formula at all, right? The parallel axis theorem at all, because the axis for the centroid of it and the centroid of the composite body are exactly the same. So all we have to do is put B, and that would be 0.05 meters. H, BH cubed, H is going to be 20 centimeters, so 0.2 meters cubed over 12. Takes care of that. I didn't actually do this intermediate part, but you know, we can do it if you want to, so why not do that? 0.05 times 0.2 to the third, all divided by 12, and I get 33 times 10 to the minus 6. All right, and that would be meters to the fourth. And then let's do, now this is going to actually be a harder one, so I want to do it underneath here. Let's do I1, and in fact I1 is going to be exactly similar to I3. So I1 actually equals I3 too, as far as the transfer and everything else. So let's just do that. So B now is 25 centimeters, so 0.25 meters. H now is 5 centimeters, so 0.05 meters cubed, divided by 12. But then we have to add the total area of these, so that's 125 square centimeters, right? Plus 125 square centimeters times the distance. Oh, you know, I say 125 square centimeters. I've already changed all of that. So I really should change the 125 square centimeters into meters. So that's 0.0125 meters. So I could 0.0125 square meters. I better write that again. 0.0125 square meters. All right. I'm going to use it again just a second anyway. Times the distance, and we know the distance is 12, so it's 0.125 meters squared. All right. And I will give you what each one of those is in just a second. 0.25 times 0.05 cubed divided by 12. Plus 0.0125 times 0.125. All of that equals, I'll try to give it to you in, well, 1.5651 times 10 to the minus 3, right? So you can see that I2, well, that's what this is. And so this is going to be times 2, right? Because we've got 3 and 1, which are exactly the same distance away, and we found their centroidal axis, the moment of inertia about their centroidal axis, and about this centroidal axis, and now we've transferred that to the center. So that's got to be times 2, because what I did was I figured this out, and I1 and I3, of course, are much larger contributors to this than the center. So let's add all of those up. I want to make sure that those come to the same answer that I have here, where I missed all of these steps. So times 2 plus 33 to the minus 6 equals, and for some reason that is not coming up to what I had. I'll tell you what, just a second, let me check some figures. I'll get right back to you. Okay, I'm back, and everybody must have seen what I did when I forgot to square the 0.125 things there. So anyway, I ended up getting this times 2 plus 33 times 10 to the minus 6 should give me exactly what I have on my sheet of paper here. 428 times 10 to the minus 6. So I total equals 33 times 10 to the minus 6 meters to the fourth plus 2 times 197.9 times 10 to the minus 6 meters to the fourth. And that gives me 428.81. 428.81 times 10 to the minus 6 meters to the fourth. So there you go. Now we have it all, and we can say that our stress, our maximum stress, and we can see a couple things. Where's this going to occur? It's going to occur right there, isn't it? I shouldn't have used that color. I should have used this color. It's going to occur right there. That's where the break is going to occur, because that's where our maximum bending moment is, right? Shear breaks occur where the maximum shear stress is. But there's almost no shear breaks that you have to worry about, and you can't learn everything in this class, but let's do this. So the maximum bending moment is 45 times 10 to the 3 Newton meters, right? Going back to what I always say, even though I don't write it down all the time. I'm always using it in my head. Times my, and y is going to be 0.15 meters, y maximum, and I have that up there too. And now we know what I total is going to be. It's going to be 428 times 10 to the minus 6 meters to the fourth. So let's throw all of those into our calculator, and I should have already had this done. I just hope that it comes out to what I have on my sheet of paper here, divided by 428 to the minus 6. And that gives me 15.771. I know I make my fives horrible, don't I? 15.771 times 10 to the 6 pascals. Well, that's pretty good. What could we use? Well, we could use steel. Could we use wood? What's the maximum normal stress for wood? That's what you're probably asking. Hey, couldn't I just nail this all together with 25 centimeters? That's like 10, a 2 by 10, isn't it? And 5 centimeters, so I've got a 2 by 10, 2 by 10. I could even throw a 2 by 10. This is an 8 by 10, 8 by 10 in there, and there you go. Then I could just use this to hold something up that's 30 meters long. That's right. If you've glued this together well and everything else and screwed it together, no problem. 15 megapascals wood can just about can take that, depending upon the kind of wood that you're using, of course. All right, that's the end of this lecture. Let's see if we can get another example of this in.